In this video, we are going to talk about side constraints. Side constraints are essentially bounds on the design variables. Just to give you a scenario you might actually encounter at some point, if you're dealing with a structural beam cross-section, you might want to vary the thickness of your cross-section. You want to make sure that the thickness is never less than 0. You can't have a negative thickness. So you might say that the design variable can be no less than 0.001 units of length. This is known as a side constraint. It's commonly known as just a bound or a limit on the design variable. So let's go ahead and walk through the process on how to create this limit on design variables. Just a quick recap. Our optimization problem statement is essentially the same as before. We have the same objective function. We're starting at the same 0.3, 4. Same design constraint, but again, we are imposing limits on the design variables. So let's go ahead and start the process in the web app. Here, I'm going to say that x1 and x2 will have limits imposed. If I look back at the plot, the limits are depicted with the dotted lines. This red dotted line here represents the lower bound for design variable x1. This purple dotted line here represents the upper bound for that same design variable. And if I zoom out, this is the upper bound for x2, this dotted line that you see me highlight. And this other dotted line is the lower bound for x2, so that would be -5. So you can see it's essentially creating a bounded box. So let's go ahead and define these side constraints or limits on the design variables. So here I will go ahead and say the lower limit is 1.5 for x1 and the upper limit is +5. I'll do the same for x2. So this is -5 and 5, and that's it. That's how you define limits on design variables. So let's go ahead and download the new zip file. And like before, we'll go ahead and start the optimization. And while the optimization is happening, we'll go ahead and look at what the solution should be. So here, let me go ahead and hide everything. What I want to do is rotate the graph and show you what is happening at the beginning. So at the very beginning, we start at the initial value of 3, 4, and the objective value is 25. So that is the value of x1 squared plus x2 squared for 3, 4. By the end of the optimization, we find that the minimum for this optimization problem statement is 1.5, 0.06, with the value of 2.25, and see if I can plot my original objective function. So here you can see what's happening. Let me zoom out just so I can rotate this. The optimizer is making a move towards the minimum here like before. So here, let me rotate this so you get a good idea. But then it encounters the lower bound of x1. Once it encounters this bound, the optimizer realizes that it still can minimize the objective. So here, this moment on the right-hand side is the moment where it touched the lower bound of x1. It then finds that it can still minimize the objective while still satisfying the side constraints. So here it's riding along the lower bound until it reaches the minimum that I showed a moment ago. So it'd be worth... Let me see if I can deselect this. Or rather than play with that, let's go ahead and look at the results here. Again, we had a value of 25 and we lowered it all the way down to 2.25. Let's look at our design variables. So here we started at 3, 4. Remember that x1 was minimized until the lower bound was touched. X1 remains at 1.5 or the lower bound for the remainder of the optimization. And for x2, you can see the value is slowly reduced until it hits a value very close to 0. So again, this video was to focus on imposing limits on what the design variables can take. In the next video, I will be discussing something that might happen quite often as a new user, and this is known as the best compromise in feasible design. So this is coming up in the next video.